So far, the examples that we've been looking at have been functions that are continuous without any domain errors. We're going to start looking at what happens if there is a domain error either for the function itself or for the derivative of the function. You're going to be responsible for coming up with the domain on your own sometimes. They might give you a domain of infinity, of negative infinity through infinity, and it's up to you to determine where the domain errors are. The first thing you need to watch for is if you have a negative under an even root. For example, if I tell you that a function is defined as the square root of x plus 4, remember the root is written on top of the radical, and when there's nothing written, it's understood to be a 2. So anytime you have an even root, 2, 4, 6, etc., you have to account for that possibility. You can take cubed roots and fifth roots of negative numbers, that's okay, but it's just when you're worried about even roots that is going to be a problem. So anytime you have a negative under an even root, there's a problem. All you have to do, this guy right here, it's called the radicand. All you have to do is set it greater than or equal to 0 and solve. So this is telling you that x has to be greater than or equal to negative 4 in order for this function to be valid. Okay, so that would be the domain. Okay, logarithms with a negative argument. Logarithm can only be taken of a positive argument. So let's say for this one we have g of x equals, we'll just use the natural log of, I don't know, x minus 4, because evidently I'm stuck on 4s. Again, this is the argument, and you just need to make sure that at this time it's positive. It can't equal 0. So I'm sorry, this is going to be x minus 4 has to be greater than 0. So for this one, we're getting x is greater than 4 as our domain. Okay. The third thing you need to watch for on either the function or the function's derivative is zeros in the denominator. Let's say we have a function h of x equals 1 over x squared, I don't know, minus 9, for example. And, you know, anytime you have a denominator, just take it and x squared minus 9, say that it can't equal 0. If you say x squared, add a 9 to both sides, x squared cannot equal 9, therefore x cannot equal plus or minus 3. Either one of those would be giving you a domain error. Okay, so that's just a brief recap of domain, which you learned in your sophomore year or your freshman year, depending on when you took algebra trig. Also, you touched upon this last year with pre-calc. So now we're going to take this and combine it with what we learned yesterday, and we're going to go ahead and use analytic methods to find extreme values. So again, we're using the techniques of calculus to tell us what's going on with the function itself. All right, so our first step is to look at the original function. Now there's no domain given for this, so we're going to have to determine the domain. I see a denominator on this thing, so the first thing I'm going to do is use technique number 3, watch for zeros in the denominators. Okay, so if I say x squared minus 1 cannot equal 0, I'm getting x squared cannot equal 1, therefore x cannot equal plus or minus 1. Okay, so that's our domain. Our original function is confined to those two values, or is confined to not be those two values, I suppose I should say. Okay, now we can go ahead and do the remainder of the problem. So to find any extreme values, you're going to set the derivative equal to 0, and you're going to find out where the derivative doesn't exist. Do you remember what those are called? Do you remember? Those are called critical points. Okay, so we're looking for critical points now. And remember, extrema won't necessarily, see, this is why I can't talk and write at the same time. I'm trying to write critical points. Extrema doesn't always have to happen where there is a critical point, but for every extrema, it will always happen at a critical point if you're talking about the interior. Okay, so it's one of those Squares, all squares are rectangles, but not all rectangles are squares. Okay, all extrema are critical points, but not all critical points are extrema. Okay, as long as you're talking about the interior of a domain. Okay, I'm done rambling, sorry. All right, so critical points. We're going to do g of x. We're going to define this no quotient rule, dumplings. Why not? Think about it, think about it. There's no variable in the numerator, so we're going to redefine g of x to be x squared minus 1 all to the negative 1 power. Now we can go ahead and do the derivative of this monkey. And it's going to be a negative 1 times x squared minus 1 raised to the negative 2 power. Don't forget the chain rule here, times the derivative of the inside, which is 2x. Because when you do things analytically, it's much easier to analyze the derivative when it is in fraction form and proper form, we're going to go ahead and clean this up. The only thing being raised to the negative 2 is that x squared minus 1. So it's now to the positive 2, and I still have a negative 2x left over. Okay? So anytime you have a fraction, the fraction is going to equal 0 where the numerator equals 0. So to find critical points where the derivative g prime of x equals 0, you're going to have this negative 2x equal to 0, and you're going to get an x of 0. That is a critical point. It is not outside of the realm of our domain. So this is a critical point. And we'll test that to be whether or not it's an extrema. Additionally, you're going to set your denominator equal to 0 to find out where g prime of x does not exist. Okay, and that happens where x squared minus 1 quantity squared equals 0, and that happens at x equals plus or minus 1. That is not part of our domain, though. Our domain that we found out at the very first part of the problem was x can't equal plus or minus 1. So these are not critical points because they are not valid points for the function. Okay, so we only have one critical point going on with this guy, and we're going to go ahead and squeeze this over here. Draw a little divider line in. Okay, let's make our little number line. And again, I apologize if I'm trying to write a little bit bigger so you can read it, but I'm hoping you have enough room. We've got, this is our x number line, and we've got at negative 1, we've got an open circle, the function's not defined there. And at positive 1, the function's not defined. So those are not going to be valid points. And at x equals 0, our derivative is 0. Okay, so at that coordinate point, and then fill that in, we've got a derivative value of 0. All right, so basically our function exists for all of these values on the x number line. We're just trying to determine what's going on with g prime. Okay, so if you test a number to the left of negative 1 into the derivative, okay, take something like a negative 2 value. If you plug in a negative 2, you're going to have negative 2 times negative 2. That's a positive number on the top, and then you're going to have a positive number on the bottom. So this region here ends up being a positive. Okay. In between negative 1 and 0, if you plug in something like a negative 1/2. Negative 1/2. So negative times negative on the top is positive. And on the bottom, you're also going to have a positive. So this is a positive as well. Okay, we know the derivative is 0 at x equals 0. In between 0 and 1, if we plug in a 1/2 again, this time we're going to have a negative on top, but a positive on the bottom. So overall, this guy is going to be negative. Okay, and then beyond 1, like at x equals 2, got a negative on top, but a positive on the bottom. This is going to be negative as well. Okay, and at x equals negative 1 and x equals positive 1, the function doesn't even exist there. And if you were paying attention last year, you'd be able to tell me what's going on with the graph if you have a 0 in the denominator. And if you didn't pay attention last year, we went over this when we talked about limits. So what's happening with the function if you get a 0 in the denominator? You go ahead, say it out loud, it's okay. That's right, it's a vertical asymptote. Okay, So if you think about this, now this is not an exact graph, but I'm just going to show, okay, here's the coordinate plane. Okay, you've got an asymptote at x equals -1. You've got an asymptote at x equals +1. To the left of -1, your function is increasing. And you would also know this is a bottom-heavy function, so it actually has a horizontal asymptote at y equals 0. In between -1 and 0, the function is increasing. So the only way it can be increasing after an asymptote is for it to be looking like this. Okay? And then it's going to flatten out and go back down, something like that, because it's decreasing after the 0 for the derivative. And then beyond the 1, it's got to be decreasing again, so it's going to look something like this. Okay, there's only one extreme value on this thing. It is a local max. There are points on the graph higher than x equals 0. There are points lower on the graph because this graph continues in both directions. So you're going to have a local max at x equals 0, and g of 0 equals -1. Okay, so that's the local max value. Values are y values. And again, we'll go through the justification of this. I'm not going to write it down, but you would write, if this was an AP exam, I got to write down because that's what I do. You would write down that g prime of x is greater than 0. Sorry, that's greater than 0 for x less than 0. And g prime of x is less than 0 for x greater than 0, indicating a max. Okay? All right, so again, I apologize for not leaving you very much room here, and I squeezed it in, but that's the gist on that problem. So again, these problems take a long time. They're very involved, lots of steps, lots of things you have to bring back from algebra and from pre-calc. But again, just go slow and we'll get lots of practice on it, okay? Okay, in example 5, we've got another function. No domain is defined, so we're going to have to figure that out first. We're asked again to find the critical points and determine extreme values. So the first thing first, I'm going to look and I see that there's an odd root. There's no even root, so I don't have to worry about any negatives under radicals. There are no logarithms of any sort, and there's no denominator at any point here. So the domain on this function is easy. It's all reals, -infinity to infinity. Okay, so we can go ahead and move on to the next part, which is to go ahead and take the derivative so we can figure out our critical points. And go ahead and shout out loud to your computer. How would you do the derivative for this thing? Okay, good. You would do the product rule. First times the derivative of the second plus the second times the derivative of the first, which is 2/3 x to the -1/3. Okay, here's an algebra alert. We're going to have to do a little bit of cleaning up before we can analyze this information. So the first thing is with the first two terms being multiplied together, the x to the 2/3 times the 2x. If you want to think about this as really being x to the 3/3, then you've got common denominators. You can add those two powers together. So 2/3 and the 3/3 makes 5/3. Give me 2x to the 5/3. And then over on the right-hand side, I've got x to the -1/3, so that's going to drop to the bottom. The 3 from the 2/3 is on the bottom, and everything else stays in the numerator. So this is going to be a plus 2 times the quantity of x squared minus 4 all over 3x to the 1/3. We're going to have to get common denominators in order to combine these two fractions together. So I'm going to multiply this guy by x, 3x to the 1/3, times 3x to the 1/3 on top and bottom. Okay, this is really over 1. So when you multiply these together, the 2 times the 3 is going to give you 6. X to the 5/3 times x to the 1/3. So nice for us becomes x to the 6/3, which is just a 2. 3x to the 1/3 here. And I'm going to go ahead and distribute this as 2x squared minus 8 all over 3x to the 1/3. And now we've got common denominators. We can combine the two together to give us 8x squared minus 8 all over 3x to the 1/3. Okay, so there's our derivative. And cleaned up and looking a little bit nicer for us. In order for an extreme value to occur on the inside of the domain, it would be at a critical point. And critical points occur where the derivative is either 0 or does not exist. So we're going to first check for y prime equal to 0. So you're just going to do 8x squared minus 8 equals 0. And you're going to get 8 equals 8x squared, which is nice for us because x is going to equal plus or minus 1. Okay, divide both sides by the 8 and then take the square root. So we've got 2 critical points out that way, possible extreme values here. And now we're going to find out where the derivative fails to exist. And that occurs when the denominator equals 0. So if 3x to the 1/3 equals 0, we are in trouble. And that occurs when x equals 0. Okay, now all 3 of these points are a part of the domain, so they are all critical points. Now we're just going to check to find out whether or not they are extreme values. So they're possible extreme values. Let's go ahead and make a number line here. We're going to have 0, we're going to have a negative 1, and we're going to have a positive 1. This is our x number line, and the domain for this function is good everywhere, so there's no problems. I'm going to just darken that, okay? Now we're going to look at our derivative, y prime of x. And we know that the derivative is 0 at 1 and negative 1. And it does not exist at 0. Now I want you to think, how could a derivative fail to exist on a continuous function? Okay, so because it's continuous, our domain, again, is negative infinity to infinity. It's not going to be a jump, and it's not going to be a vertical asymptote. So there are 3 possibilities now for how the derivative can fail to exist. And those 3 possibilities are a cusp, a corner, or a vertical tangent. And we'll be able to kind of figure out if it's a cusp or a corner versus a vertical tangent in just a second. So now we need to test our regions. Again, we're finding out what's going on with the derivative, so we're plugging values into the derivative. Okay, so we're checking values into this guy over here. All right, so if we test something like a negative 10 and we plug that in, we're going to get negative 10 squared, which is positive 100 times 8. So that's a positive number on the top, but we're getting a negative number in the denominator. So a positive over a negative makes a negative. Would you like that? Shake the paper a little bit. All right, in between negative 1 and 0, if we plug in something like a negative 1/2, negative 1/2 when you square it is going to give you a positive 1/4. 8 times a fourth is 2. We're ending up with a negative on the top, a negative on the bottom, which makes a positive overall. Okay. If you need to go a little bit slower so that you can figure out the values, hit pause right now and go back and do that and make sure you understand why this is a positive in that region. Go ahead and do the same thing right now for in between 0 and 1 and beyond 1. I want you to test regions, plug in numbers into the derivative, and tell me what you get. Go ahead and hit pause. Do this now. Okay, if you had plugged in something like a 1/2, again, you plug in the 1/2, you square it, you get a 1/4. You're getting a negative on the top, but a positive on the bottom. You're ending up with a negative. And for beyond 1, we're getting a positive number out of the numerator and the denominator. Okay, so what does that tell us about our function? Well, that means that our function is starting off by it's decreasing, then it's increasing, and there's a smooth transition because it does have a derivative value of 0 at -1. So if I was, again, I'm just guessing, I don't know the exact values here. I'm just trying to get an idea of what's going on. But I definitely, I've got decreasing, then increasing. So at x equals -1, I've got a min. And so let's go ahead and find out what that value is anyways. So if you plug in y of 1, you're going to get 1 to the 2/3, which is just 1. And then you're going to have 1 squared minus 4. So again, I'm plugging back into the original up there. So you're getting a -3 value out. So it's supposed to be a -1, isn't it? Okay. You're actually getting a +3 out. Right? Let's see, -1 squared. That's a positive. And then -1 squared minus 4. Oh, this is a -1, or a -3, pardon me. So it's y equals y of -1 is -3. So at -1, you're getting a -3 value out, something like this. So it's decreasing to this point, and then it's increasing. Okay. At x equals 0, we've got a max, right? If you've got a decreasing or an increasing function going to a decreasing function, right? So again, if it helps you to write this, y is decreasing, then it's increasing, then it's decreasing, then it's increasing. Okay, so this is going to have to be a min, this is going to have to be a max, this would have to be a min. Okay, so let's go ahead and check out what's going on as far as the max is concerned. Y of 0 is going to equal 0. So it comes up to here. Now the only way that this can come up to 0 and then decrease without there being a level spot is for this thing to have a corner or a cusp. Okay, so I'm going to draw it as a cusp. It doesn't matter because, again, we're just trying to get an idea. We have another minimum, y of +1. Y of +1, 1 to the 2/3 power is 1. 1 squared minus 4 is going to be -3. So that's a -1. This was 1. We're getting something like this. And then it increases afterwards. Okay, so this is a rough idea of the graph. And again, you would justify this using sentences talking about the derivative being negative and then positive, which means you've got a min. The derivative being positive, the negative, which means you've got a max. So that's the gist. We'll practice a lot more tomorrow. Go back and rewatch anything that you need to, and I hope you guys have a wonderful evening. Okay, talk to you later. Bye.